All right, so I hope we can start. Who can remind us of what we treated last week?
Vacuum tubes.
Okay, so what are vacuum tubes? Yes, we are listening. Just tell us whatever you can remember.
They allow thermionic emission of electrons. They have electrodes in them.
Okay. What are their uses? Uses of vacuum tubes. No one can remember any of the use of vacuum tube.
Can be used as amplifiers.
Okay. Give us, someone else should tell us one or two advantages of vacuum tube. One or two advantages of vacuum tube.
They can be easily replaced.
All right. Disadvantage.
Consume a lot of energy, sir.
Okay, that is nice. Types of vacuum tubes. How many?
4. 4, sir.
Mention them.
We have the diode, we have the triode, we have the
Tetrode and pentode.
yes, tetrode and
Right.
pentode.
So, what is the advantage of triode over diode? Then tetrode over triode and pentode over the others.
That triode has an additional electrode called a control grid.
Okay.
Pentode, I think it has a
The advantage of that over. So if you, yes, if you just mention that it has additional electrode, that one is not an advantage.
For triode over diode, triode can amplify weak electrical signals as opposed to diodes.
Pentode and triode, I mean tetrode and triode.
Tetrode has a screen grid as to tetrode, which has only control grid.
God, I beg. Okay,
A tetrode has a screen grid
Okay.
which accelerates the speed of electrons.
Okay.
they also have improved stability,
Okay. So what is
which
the
makes
disadvantage?
them less
Less what?
It
Which
makes them more
makes
energetic.
them
energetic.
Do they have disadvantage?
Yes, they lead to secondary emission, which leads to release of electrons from the electrode.
All
true.
right.
It's just what
So pentode.
Going to that suppressor group.
Pentode. Continue. We are
So
listening.
the pentode, it has a suppressor group that is used to repel any form of secondary emission.
All right. Is there any disadvantage with pentode?
No, sir.
To the best of your knowledge? So pentode is perfect. Is that what you mean?
For now.
For now. So if pentode is perfect, why do we need to go ahead to get a transistor?
So they will require higher grid currents. I think
some of the disadvantages of pentode is higher cost. So
Okay,
yes.
and what else?
I think it requires higher grid currents, sir.
It generates a
then
lot of heat.
they generate much
Higher grid
noise.
currents.
Higher distortion.
Okay.
They generate much noise and then difficulty in biasing.
Difficulty in biasing. How?
Yes.
How?
Trying to the proper biasing can be difficult, especially when it comes to high gain applications.
Are you sure of what you're saying? So what is biasing? You are the one that mentioned biasing. What is biasing?
The adding of external voltage to the diode sound.
Okay. So you have all tried. Let's continue with today's class. So today we are moving on to semiconductors, which replace vacuum tubes. Semiconductors which replaced vacuum tube because of the disadvantages of vacuum tubes. So normally, materials are classified into three categories. We have the insulator, we have conductor, and we have semiconductors. Based on in whatever category you want to divide them, three. Let's take three for now. So we have insulators. Insulators, like we define, have the electrons within them are bound to the system. So because of that, there is no free movement of electrons. And so when electrons are not moving from one point to another, current will not flow. The movement of electrons is what constitutes current. So for insulators, the electrons are bound to their crystal lattice. So because of that, the electrons are not free to move. So they can conduct current and heat readily. While for conductors, they have excess free electrons. So even without application of any source of energy, voltage in terms of heat, electricity, light, that is the four sources of energy to make an electron escape from the surface. Light, heat, secondary, that is by kinetic energy, and electric field. Electrons in conductors will still be mobile. They will move from one point to the other. So while they are moving, like I said before, they are not free to leave the surface of the material, except they acquire additional energy that is greater than the surface barrier before they move away from, or before they are emitted away from the surface. So they conduct electricity and heat, whether at room temperature or at any temperature. They are, because of their free electrons. Now, the third category, which is semiconductors. Semiconductors are, they have properties between insulators and conductors. So at a particular time, they behave as an insulator, and at a particular time, they behave as a conductor. So when they are at 0 degrees Celsius, they behave as an insulator. But when the temperature of the semiconductor material is raised up to room temperature, they begin to conduct and behave like a conductor. So that is a brief introduction about the classes of materials that we have. So certain substances like germanium, silicon, carbon are neither good conductors like copper, nor insulators like glass. In other words, the resistivity of these materials lies in between the conductors and insulators. So such substances are classified as semiconductors. Semiconductors. A transistor is a semiconductor device. We have diodes. Transistor is made from 2 p-n junction diodes. Now, a semiconductor is a substance which has resistivity of 10⁻⁻⁴ to 0.5 ohm meter. 0.5 ohm meter. So here we have the conductivity of different materials. We have copper. Copper has a conductivity. It's a very good conductor, has a resistivity of 1.7 × 10⁻⁻⁸ ohm meter. Germanium has a resistivity of 0.6 ohm meter. Is classified as a semiconductor. And then glass is an insulator which has a resistivity of 9 × 10⁻11 ohm meter. Nichrome is a resistant material which has the resistivity of 10⁻⁴ ohm meter. Now, some properties of semiconductors. The first one is that the resistivity of a semiconductor is less than an insulator, but more than a conductor. So if you look at this, you see semiconductor is 0.6, which is far less than an insulator, 9 × 10⁻11. but is more than a copper, which is a good conductor, 1.7 times 10 raised to minus 8. The second point there is semiconductors have negative temperature coefficient of resistance. That is, the resistance of semiconductor decreases with increase in temperature and vice versa. So like I stated before, I said at 0 degrees, semiconductor behaves like an insulator. And then at room temperature, they behave like a conductor. So if one is tempted to begin to increase the temperature, thinking that, oh, they are now
So can you?
if you are tempted to raise the temperature of the semiconductor further, hoping that the more you increase the temperature, like a conducting material, when you increase the temperature, the rate of emission or conductivity increases with increase in temperature. So semiconductor will increase up to a certain level. After room temperature, it will begin to behave abnormally. So that is why it has a negative temperature coefficient of resistance. The third point is when a suitable metallic impurity is added to the semiconductor, its current conducting properties change appreciably. So the problem with negative temperature coefficient of resistance is to an extent addressed by the third point. So here, the third point is what we refer to as doping. Doping, that is addition of impurity to a pure semiconductor material. So when we add an impurity, the impurities are not just dust or sand particle outside. They are still materials like arsenic or gallium and so on. Phosphorus is there, aluminum is there. That's group 5 elements and group 3 elements. Those are the materials we are referring to as impurity. So when these impurity, metallic impurities are added to a semiconductor materials, it raises the conductivity. It makes the semiconductor to function properly, So that leads us to types of semiconductor. So there are 2 types of semiconductor. The first one is intrinsic semiconductor. The second is extrinsic semiconductor. Intrinsic semiconductor is semiconductor in an extremely pure form. That is, in its pure form. No impurity has been added. It is totally pure semiconductor that behaves as insulator at 0 degree and as a conductor at above room temperature. So this is intrinsic semiconductor. In intrinsic semiconductor, the charge carriers, remember that in a semiconductor, we have both positive and negative charge carriers. Positive and negative charge carriers. So the charge carriers, the positive and negative charge carriers are equal. The positive and negative charge carriers are equal in a semiconductor, intrinsic semiconductor material. So in an intrinsic semiconductor, even at room temperature, all electron pairs are created. And when electric field is applied across the semiconductor,
We can't hear you, sir.
takes place by two processes. So here we have a diagram showing us about intrinsic semiconductor. The two processes, which are the free electrons moving and the holes accepting the free electrons. The free electrons are produced due to the breaking up of some covalent bonds by thermal energy. At the same time, holes are created in the covalent bonds. So when an electron is excited from a surface, it migrates to another level. That is, you remember we talked about energy level, the principal quantum energy level, that is KLM and so on. So when electrons move from one energy shell to another, it creates a hole there. It creates a hole. And so another adjacent electron will move to fill that hole. So under the influence of electric field, conduction through the semiconductor is by both free electrons and holes. Therefore, the total current inside a semiconductor is the sum of electrons and holes. Electrons and holes. That is the total sum of current in a semiconductor. However, in a conductor, we have just one current. That is a conduction by electron. But in semiconductor, we have two currents, conduction by electron and conduction by holes. That is the total, to make the total current. Now, in an intrinsic semiconductor is formed when we add impurity, like I mentioned before, group 3 element and group 5 elements. Remember, group 3, they have 3 outer shell electrons. Group 5, they have 5 outer shell electrons. So semiconductors has 4 electrons. If group 5 and semiconductors are in group 5, so 5 electrons and 4 electrons coming together. Remember, in your chemistry, you will strive to form an octet, 8 in number. So when 5 and 4 comes together, will form a stable octet, and 1 electron will be in excess. So that electron is what will go into operation, into conduction. And because it is electron, that semiconductor that is formed with group 5 electron, group 5 elements, is referred to as N-type semiconductor. N-type semiconductor. When a group 5 metallic impurity is used as a dopant for a semiconductor material, the semiconductor material formed in that case is referred to as N-type, because there is 1 extra electron that goes into conduction. So N-type is formed. Now, when we dope a semiconductor with a group 3 impurity, we are going to form 7 outermost electrons. In this case, we are not able to achieve a stable octet. So we formed 7. It means there is 1 space left to form a stable octet. That space is what is referred to an extra hole. So this kind of semiconductor is referred to as p-type semiconductor. P-type semiconductor, because holes are given a positive sign. So because since we have holes in that semiconductor formation, we are going to call it a P, or it is called a p-type semiconductor. So extrinsic semiconductors are divided into or classified into 2 types: N-type semiconductor and a p-type semiconductor. So I've explained to you how how N-type semiconductor is formed and how a p-type semiconductor is formed. So here you have the explanation and the diagram. So if you look at this diagram, you'll see the free electron at the center here. Free electron at the center. Arsenic is group 5 impurity. We have germanium group 4. So when we dope a germanium semiconductor with arsenic impurity, pentavalent impurity, we are going to have N-type.
Sorry, sir, seems a hand is raised.
Now, the current conduction in an N-type semiconductor is predominantly by free electrons. That is negative charges, and is called N-type or electron type conductivity. When PD is applied across the N-type semiconductor, the free electrons donated by the impurity in the crystal will be directed towards the positive terminal, constituting electric current. So the addition of pentavalent impurity has produced a number of conduction band electrons. So if you look to the left diagram, we have 2 energy bands there. We have the valence band and we have the conduction band. We have the valence band and we have the conduction band. For an intrinsic semiconductor, we have equal number of electrons and holes. The conduction band basically contains electrons, while the valence band contains holes mostly. So the number of electrons in an intrinsic semiconductor is equal to the number of holes. But in extrinsic semiconductor that we have here before us, we have more electrons than holes. We have more electrons than holes, and the electrons will occupy the conduction band. That is where they conduct. That is where they operate. That is where they move from one place to the other. They are excited from the valence band into the conduction band. Now, in the conduction band, we have fewer holes. Fewer holes. Unlike intrinsic Unlike intrinsic, we have equal number of electrons and holes. But here now, we have more electrons than holes. We have more electrons than holes. So, nevertheless, in N-type semiconductor, remember, since it is a semiconductor, conduction is by electrons and holes. Anything semiconductor, the conduction is by electrons and holes. Now, for intrinsic semiconductor, they are equal. The number of electrons is equal to the number of holes. But for extrinsic semiconductor, they are not equal. For N-type, the number of electrons are more than the number of holes. For P-type, the number of holes are more than the number of electrons. So in N-type, we call electron the majority carrier. For N-type, we say that electrons are the majority carriers, while the holes are the minority carriers. And similarly, for P-type, holes being more than electrons are the majority carriers, while electrons are the minority carriers. So when voltage is applied across both ends, the electrons migrate to the positive terminal. Now, not just because voltage is applied to both sides, the voltage must be applied in a way that the electrons will migrate to the positive terminal. That is called forward biasing. If I applied my voltage in a way that I have the negative terminal to the N-type, okay, let me not jump the gun. We'll get to that point. So let's still continue with. So I've explained this also for P-type, when trivalent electrons or impurities, trivalent impurities or atoms are added to a pure semiconductor, P-type semiconductor is formed. However, even though P-type semiconductor is formed, we'll still have electrons within that type. So, but the majority carrier is P-type, that is hole. Majority carriers are holes, while minority carriers are electrons. Look at this. Let me bring your attention to something here. Okay. Now, the arsenic, that is the pentavalent impurity atom, is referred to as donor impurity. It's also referred to as donor impurity because they donate their electrons. They provide their free electrons to the semiconductor crystals. But for P-type, the impurities are referred to as acceptor impurities because the holes created can accept the electrons. So note that examples of trivalent impurities are gallium and indium. Gallium and indium. Here, when current, okay, the current conduction in P-type is predominantly by holes. That is, majority charge carriers in P-type is holes. And we also have minority charge carrier in P-type as electrons. When PD is applied to the P-type semiconductor, the holes that is donated by the impurity are shifted from one covalent bond to another. Now, take note of that word, shifted. Shifted is different from moving. In reality, holes does not move. Only electrons moves. The electron moves to replace, to fill holes. For instance, look at, I hope you are seeing the mouse here, the mouse pointer here.
Yes, sir.
Look
Yes,
at
sir.
this part where I'm pointing. For instance, if an electron jump from this point across, this is the valence band, across to the conduction band, it will create a space that is a hole here. Then this next electron here will move, jump into this hole to fill this hole here. The next electron here, then here there will be hole. The hole is no more here. The hole is now here. This electron will jump to fill this hole. There will be hole here now. The hole has moved to this point. This electron here will jump to fill this, creating a hole here. The electron here will jump to fill this, creating a hole here. The electron here will jump to fill this hole, creating a hole here. And the electron here will jump to fill the next hole. And so it is. So the electrons keep jumping across while the other adjacent electrons will move forward to fill the holes. So before you know, the hole that used to be in front here will appear at the back and spread. As the more the electron jump across, the more the hole spread. So it's as if the hole is moving from the back to, that is from the right side to the left side, but holes does not actually move. It's only electrons that moves. When they move from one point to the other, they leave behind a hole. So that is how it works. But we just assume that the charge carriers are holes and electrons. But in reality, it's only electrons that moves from one place to the other. Now, I've talked about this majority and minority carrier. In N-type, we have majority carrier as electrons and minority carrier as holes. The diagram to the left is showing that we have more of electrons in that diagram than holes. And then to the right side, which is P-type, we have more holes, which are majority carriers, than electrons, which are minority carriers. So electron and hole mobility. Electron and hole mobility. So drift velocity is directly proportional to electric field. Hence, when the electric field increases, drift velocity also increases. However, mobility of electrons is independent of applied electric field. That is, change in electric field does not change the mobility of electrons. Remember that electrons are constantly moving in a conductor, whether there is an applied electric field or there is no electric field. the electrons will continue to move because they are free electrons. So here we have our first formula to calculate electrons. I mean, to calculate the current in a semiconductor. So we have, or in a material, let's say in a material, I is equal to N A V Q. N A V Q. N for I for current flowing through the conductor, which is measured in ampere. N for number of electrons. A for the cross-sectional area of the conductor. And V for the drift velocity. Drift velocity. From the word drift, that is moving, migrating, moving from one point to the other. The speed at which electrons move from one point to the other, we call that as drift. So Q is the electron charge. Sometimes you will see Q as small letter E. Small letter E is electron charge. It's a constant value. 1.6 times 10 raised to minus 19 coulomb. Minus 19 coulomb is a constant value. So here we have an example. Consider a current of 3 ampere that is flowing in a copper conductor. Flowing in a copper conductor with a cross section of 1 millimeter square. 1 millimeter square. You are asked to find the speed, that is the velocity, the drift velocity. So the first thing to do is to write down the formula and then note the other parameters that are given. N, which is the number of electrons in copper, is given to us here as 8.5 times 10 raised to 28 per meter cube. The current is given to us as 3. Then the cross-sectional area is the cross-sectional area is given to us as 1 millimeter square. Now, if you look at this question, area was not mentioned, but you'll see that we have a copper conductor with a cross-section of 1 millimeter square. Remember that the unit, sometimes when you are confused of a particular parameter, use the unit to trace it. The unit of area is meter square or centimeter square or millimeter square. So in this case, we have 1 millimeter square. But because the other parameters are in fundamental units, we have to convert this also to fundamental unit. And that gives us 1 times 10 raised to minus 6 meter square. Minus 6 meter square. So if you substitute and make V, drift velocity, the subject of the formula and solve, you have 2.2 times 10 raised to minus 4 meter per second. Minus 4 meter per second. Now, relationship between drift velocity and current density. Remember, we did this under Richardson-Dutchman equation. current density is equal to current times area. So if current density is equal to current times area, and we know that current is equal to NAVQ, so we can replace current as NAVQ over A, NAVQ over A, and that gives us NVQ. Sometimes I used to write it as never. I prefer this because if you forget formula, it's easier to remember when you have used the acronyms to represent it. So this is NEV. So E is electron charge, which we know that is a constant, 1.6 times 10 raised to minus 19 coulomb. So this is how they are related. The current density is directly proportional to drift velocity. So they as the rate of the electrons increases in terms of velocity, as their speed increases, the current density will also increase. Remember that current density is also directly proportional to current. So when current increases, current density will increase. And when the speed of electron, the rate at which they move from one point to the other increases, the current also will increase and the current density will also increase. Electron mobility. The ability of an electron to move through a metal or semiconductor in the presence of applied electric field is called electron mobility, and is given there as V subscript N, which is drift velocity of the electron, is equal to mobility of the electrons times the applied electric field. So the drift velocity is directly proportional to the applied electric field. So if drift velocity is directly proportional to the applied electric field, the more the electric field, the more the electron drift from one end to the other. And that itself is what we refer to as electron mobility. Now, for a semiconductor that consists of large number of free electrons, when there is no voltage or electric field applied across the semiconductor, the free electrons moves randomly. Let's say this particular semiconductor is mobile, that is at room temperature. So the electrons within the charge carriers within the semiconductors are moving on their own. But without application of electric field, they will move randomly. There will be no well-defined path. However, when the voltage or electric field is applied across the semiconductor, where you will just notice that the path in which the electron flows or move will not be defined. They will all move in a straight line, migrating towards the opposite terminal. So that is what you see here. You see here, look at the conduction band and the valence band. We have electrons and holes in both bands, But because there is no application of electric field, they are moving randomly. But in the second diagram here, a voltage has been applied. That is, an electric field has been applied across. So you see them becoming orderly. So they are moving from one end to the other on a straight line. So that is what this particular part is referring to. Whole mobility. Just like we have electron mobility, we also have whole mobility. The ability of an hole to move through a metal or to shift from one end of a metal to the other. Or semiconductor, not metal, it should not be a metal. Metals does not show that they have holes. That is why it took time it was until semiconductors were discovered before we knew that there are other second charge carrier in the name of hole. So, so drifting or moving through a semiconductor in the presence of electric field is called hole mobility. And the formula is similar. The only difference is the subscript, it changed to P for holes, while the subscript it changed to why the subscript is N for electrons. For holes, the subscript it changed to a P. Let's look at some application of semiconductors, and we'll end the class here for today. By next week, we should be planning to, let's see how far we'll go. I still want to introduce some calculations on semiconductors. And notice that it's not in the slide. So applications of semiconductors. Semiconductors are used in almost all electronic devices. Without them, our life would be much different. Their reliability, compactness, low cost, and controlled conduction of electricity make them ideal to be used for various purposes in a wide range of components and devices. Transistors, diodes, photosensors, microcontrollers, integrated chips, and much more are made up of semiconductors. Uses of semiconductors in everyday life. Temperature sensors are made with semiconductors, like our infrared temperature or sensor, or infrared thermometer that was used during the COVID, that became so popular. Anywhere you go, you see that before you enter any meeting where there is a public gathering, you see someone checking the temperature of people using infrared. Of course, that is safer than mercury in glass thermometer, where they will have to put that, and that means that the person will be in physical contact with you. So it's with the help of semiconductor that device was manufactured or produced. They are used in 3D printing machines. 3D printing machines used in microchips and self-driving cars, using calculators, solar plates, computers, laptops, and other electronic devices. Your cell phones, they are all made up of semiconductors. Then transistors and MOSFET used as switches in electrical circuits are all produced using semiconductors. Industrial uses of semiconductors. The physical and chemical properties of semiconductors made them capable of designing technological wonders like microchip transistor LED, that is LEDs, and solar cell. All around us, we have flat screen, and so many of them. Microprocessors used for controlling the operation of space vehicles, train, robots, etc. It's made up of transistors and other controlling devices, which are manufactured by from semiconductor material. So importance of semiconductor materials, they are highly portable due to the smaller size. They require less input power. Semiconductor devices are shock-proof. They have a longer lifespan. They are noise-free while operating. So these are advantages over vacuum tubes. These are all advantages over vacuum tubes. So that is the end of our class for today. So hopefully we have one more class, one or two more classes on my part. Then the next person will take over from me. Any question? So I have only 42 names here registered as for attendance. Only 42 send their names, matric number, and department. So I'll take that as attendance, that for today, only 42 students attended the class. So have a lovely weekend. In the absence of no question.
You too, sir. Have a lovely weekend, sir.
Thank you very much.
Have a lovely weekend, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Can tell me that.
Sir, for the attendance, there are more names at the top. Like, the list is not complete. We are more than 42. Hello, sir.
You don't go shop, leave am. You don't go find food shop.
Why would you talk to your lecturer like that? Ladipo, lead the